Right now, 400 million kilometers from Earth, something is moving through our solar system that shouldn't exist. When it approaches the Sun, it develops a tail of gas and particles pointing away from the Sun. Away from the Sun. That's not a minor detail, that's the signature characteristic that separates comets from asteroids, from spacecraft, from every other category of solar system object. The tail points away because of solar wind pressure and solar radiation pressure. This isn't theoretical physics. This observation is confirmed 10,000 times over centuries of watching these objects. Hit like and subscribe for more sleepy explanation. When a comet heats up near the Sun, frozen materials on its surface sublimate, turning directly from solid to gas. This creates the fuzzy atmosphere called a coma. The solar wind, just moving at 400 to 800 kilometers per second, slams into this material and blasts it backward, away from the Sun. Always, without exception. The physics doesn't care about the comet's composition, its size, or where it came from. The solar wind is relentless. It's a stream of charged particles, mostly electrons and protons, erupting from the Sun's corona with enough force to shape the entire heliosphere. When these particles hit gas molecules from a comet, they ionize them and sweep them into the characteristic ion tail, which always points precisely away from the Sun. When solar radiation hits dust particles, radiation pressure pushes them backward too, creating the dust tail, which curves slightly because the particles have mass, but still sweeps generally away from the solar direction. This is first semester astronomy. This is what comets do. 3I Atlas has a tail pointing at the Sun, not sort of toward the Sun, not in a direction that could be explained by viewing angle, directly at the Sun. A massive, persistent structure of material flowing sunward, while every law of physics we understand says it should be impossible. Now before you say, anti-tails exist, yes, they do. And we need to talk about that because the mainstream explanation for Atlas's anti-tail relies on those documented cases. True anti-tails are incredibly rare, and when they do appear, they're almost always optical illusions created by geometry and perspective. Here's how a perspective anti-tail works. When Earth's orbit crosses the orbital plane of a comet, our viewing angle changes dramatically. For a brief period, maybe a few days, as dust particles that the comet has spread along its orbital path can appear to be in front of the nucleus from our perspective, creating the illusion of material pointing sunward. It's like looking at a highway from ground level versus from a bridge. The perspective shift makes the same objects appear in different positions. These perspective anti-tails are well understood. They last for days, not months. They appear only during specific geometric alignments between Earth and the comet. They're subtle, faint, and they disappear as soon as the viewing geometry changes. 3I Atlas's anti-tail is none of those things. It has persisted through multiple observation sessions spanning months. It maintains its sunward orientation regardless of Earth's position. It's not faint or subtle. It's a dominant structural feature visible in every properly exposed image, and most critically, it shows no sign of being affected by the solar wind that should be annihilating any material attempting to move sunward. Think about what's required for material to point toward the Sun against solar wind. You need a force stronger than the wind itself. On a comet, the only force that could possibly overcome solar wind is outgassing from the nucleus. Gas erupting from surface vents with enough velocity to overcome the opposing pressure. But here's the problem with that explanation. Outgassing produces a mix of particle sizes. When a comet's ices sublimate, they release not just gas molecules but dust grains of varying sizes. The smallest particles, micron-sized, get swept away by solar wind immediately. Medium particles get pushed back by radiation pressure. Only the largest particles, maybe millimeter to centimeter scale, might resist the wind for any distance. So if outgassing is creating Atlas's anti-tail through large dust particles that can resist solar wind, where is the conventional dust tail made of the smaller particles? Where's the ion tail made of the gas molecules? Every real comet with strong outgassing shows multiple tails, because outgassing produces multiple size fractions of material. You get the bright ion tail of ionized gas, you get the broad dust tail of fine particles, and maybe, if conditions are just right and you have huge boulders being ejected, you might get some large debris that doesn't get swept back immediately. Atlas shows the anti-tail and nothing else in that direction. No conventional tails. No evidence that the solar wind is having any effect whatsoever on this object's emissions. Let me show you what a real comet looks like. C/2014 Q2, Comet Lovejoy. This object came from the Oort cloud, the same distant reservoir that supposedly birthed Atlas. Lovejoy was weird. It had an unusual composition rich in organic molecules that gave it a characteristic green colour. Its coma showed complex knotted structure. Multiple jets erupted from its nucleus in asymmetric patterns. By all accounts, Lovejoy was an oddball comet. Unusual chemistry, complicated outgassing, active jets creating intricate patterns in its coma. But look at what happened to those jets when they hit solar wind. Every single stream of material, regardless of its composition, regardless of which direction it initially erupted from the nucleus, got bent backward. The jets start out oriented in various directions based on where the vents are on the nucleus. But within a few thousand kilometers, solar wind dominates. The material streams backward, away from the sun, exactly as physics predicts. The Larsen-Sechenina filter, which enhances subtle structure in cometary comas, shows this clearly. You can trace individual jets back to their source points on the nucleus. You can watch them curve as solar wind pressure overcomes the initial outgassing velocity. You can see the dust and gas separating into distinct tails, as different particle sizes respond differently to solar forces. Lovejoy had organic chemistry that Earth-based comets don't show. It came from the frozen outer reaches of our solar system. It was active, dynamic, unusual, but it obeyed physics. The solar wind bent its jets. Radiation pressure shaped its tail. It behaved like a comet because it was a comet. Now look at Atlas in the same type of enhanced imagery. The anti-tail doesn't bend. The additional jets don't curve. There's no evidence of solar wind interaction at all. The material flows in straight lines, maintaining its orientation across hundreds of thousands of kilometers, as if the sun's radiation simply doesn't exist. Let me show you another example. Comet with 3 distinct tails. The narrow straight one is the ion tail, composed of ionized gas molecules that align with magnetic field lines in the solar wind and point precisely away from the sun. The broader fan-shaped structure is the primary dust tail, particles of varying sizes all being pushed backward by radiation pressure. And the third tail, slightly offset, is a secondary dust tail, phased probably from a separate outgassing event days or weeks earlier. 3 tails, 3 distinct populations of material, all of them obeying the same physics, all of them streaming away from the sun. This is what normal comets do when they have multiple jets and complex outgassing. They create multiple tails, but all those tails respect the solar wind. The material might start out going in different directions as it leaves the nucleus, but within a short distance, solar forces dominate and everything bends backward. Atlas has 3 or 4 distinct tails depending on when you observe it. None of them point away from the sun. None of them show any sign of bending or curving in response to solar wind. They maintain perfect geometric separation. Like the object is emitting material through precisely engineered ports, rather than through natural outgassing from a chaotic, irregular surface. The mainstream explanation for Atlas's anti-tail relies on something we've never actually observed before. The theory goes like this. Atlas is producing unusually large dust particles during outgassing. These particles are so massive that solar wind and radiation pressure can't affect them. They maintain their outward trajectory from the nucleus for hundreds of thousands of kilometers, creating the anti-tail. This explanation has problems stacked on top of problems. First, outgassing doesn't selectively produce only large particles. When ices sublimate from a comet's surface, the process breaks material into a range of sizes. You get individual molecules of gas. You get microscopic grains of dust that were embedded in the ice. You get larger chunks that break off as the ice sublimates around them. It's a spectrum, not a single size class. For Atlas to show only large particles in its anti-tail, the outgassing process would need to somehow filter out everything smaller. Gas molecules would need to stay on the nucleus instead of escaping. Fine dust would need to be prevented from mixing with the large grains. This doesn't match any outgassing mechanism we understand. Second, even large particles aren't immune to solar forces indefinitely. Sure, a centimetre-sized chunk of ice and dust might resist solar wind better than a micron-sized grain, but over distances of hundreds of thousands of kilometres, the cumulative effect of radiation pressure adds up. The particle should gradually decelerate, and its trajectory should curve, even if the curve is gentler than we'd see with fine dust. Atlas's anti-tail shows no curvature. The material maintains a straight line pointing directly at the sun across the entire observable length of the tail. If these are large particles coasting on their initial outgassing velocity, why don't we see them slowing down? Why don't we see the tail bending even slightly as radiation pressure accumulates over time? Third, and most critically, if outgassing is producing large particles that create the antitail, where are the small particles? They have to exist. Sublimation produces them. So where's the conventional dust tail made of fine grains? Where's the ion tail made of gas molecules? You can't have outgassing that produces only large particles. That's not how the physics works. If the nucleus is active enough to eject centimetre-sized chunks at velocities high enough to overcome solar wind, it's definitely releasing gas molecules and fine dust too. Those lighter components should create visible, conventional tails streaming away from the sun. They're not there. What we're seeing is an object that appears to be emitting material through some process that doesn't match cometary outgassing. A process that produces narrowly confined streams of material. A process that imparts enough velocity or momentum to that material to completely ignore solar wind. A process that creates geometric precision instead of chaotic spray. Comets rotate. This isn't controversial. Every comet we've ever studied in detail shows rotational periods ranging from hours to days. The nucleus is typically an irregular chunk of ice and rock, or is tumbling through space, and that tumbling affects how material escapes from the surface. When a comet rotates, its jets rotate with it. Imagine a garden sprinkler spinning in your yard. The water comes out in a focused stream, but because the sprinkler head is rotating, that stream sweeps across the lawn in an arc. You don't get a single straight line of water, you get a fan-shaped spray pattern as rotation carries the outlet around. Comet jets work the same way. A vent on the nucleus releases material in a particular direction based on the local surface orientation. But because the nucleus is rotating, that vent sweeps across space, and the jet creates a curved, fan-shaped structure in the coma. This is one of the most distinctive features of active comets. The jets fan out. They create spiral patterns. They show clear evidence of being affected by rotation. Look at comet Shengshan Atlas, discovered by the same telescope system that found 3I Atlas. Multiple jets, complex structure, beautiful patterns in the coma. But look at the geometry of those jets. They're fanning out. They're curved. They're creating exactly the pattern you'd expect from jets on a rotating nucleus. The rotation period of Shengshan Atlas is about 10 hours. You can trace each jet back to its probable source location on the nucleus, and you can see how rotation has swept that jet across space, creating the observed fan structure. This is textbook cometary behavior. This is what jets on rotating nuclei do. 3I Atlas rotates approximately 3 times per day. That's a period of about 8 hours, similar to Shengshan Atlas. And Atlas has multiple jets just like Shengshan Atlas. But those jets don't fan out. They don't show spiral structure. They maintain straight-line geometry as if rotation isn't affecting them at all. How is that possible? There's actually one scenario where jets can remain relatively straight despite rotation. If the vent is located very close to one of the rotational poles, the sweeping motion from rotation is minimal. Imagine that garden sprinkler again. If the outlet is right at the central axis where the rotation happens, it barely moves as the sprinkler spins. A vent at a comet's pole would behave similarly, producing a jet that wobbles slightly but doesn't sweep across space in a wide fan. So maybe Atlas's jets are coming from near the poles. That would explain the straight-line geometry. In fact, there's some evidence for this. The anti-tail shows a slight wobble in its orientation, consistent with the source point about 8 degrees from one of the rotational poles. 8 degrees off pole would create observable wobble, but not the dramatic fanning we see with the equatorial jets. Okay, so the anti-tail is coming from near a pole. That's unusual but not impossible. Problem solved, right? Not even close. Because here's what makes this completely inexplicable. Atlas passed perihelion. It swung around the sun. And when an object passes perihelion, its orientation relative to the sun changes dramatically. Think about Earth's seasons. Our axis is tilted relative to our orbit around the sun. When we're on one side of our orbit, the North Pole tilts toward the sun, giving us summer in the northern hemisphere. 6 months later, when we're on the opposite side of our orbit, the North Pole tilts away from the sun, giving us winter. The orientation of our axis relative to the sun has changed by a full reversal. The same thing happens when a comet goes around the sun. Its rotational axis maintains the same orientation in space, but because the comet is now on the opposite side of the sun, The pole that was previously tilted sunward is now tilted away, and vice versa. For Atlas, passing perihelion meant the orientation of its poles relative to the Sun shifted by about 16 degrees based on its orbital geometry. If the anti-tail was coming from a point 8 degrees off one pole before perihelion, that source point would no longer be oriented toward the Sun after perihelion. And yet the anti-tail persisted after perihelion with the same orientation. Let that sink in. The only ways this works are 1. The nucleus adjusted its rotation axis by exactly 16 degrees during perihelion to keep the same vent oriented toward the Sun. Natural tumbling doesn't do that. You'd need an applied torque to shift a rotation axis, and there's no source for such a torque. 2. There just happens to be an identical vent on the opposite pole, also 8 degrees off axis, that started producing the anti-tail post-perihelion with the exact same characteristics as the pre-perihelion tail. The odds of that are astronomical. Comet nuclei are irregular, chaotic surfaces. Having two vents in geometrically perfect positions on opposite poles that produce identical outflows is not how nature works. 3. The anti-tail isn't coming from natural outgassing at all. It's being produced by something that can maintain orientation regardless of the nucleus's rotation or orbital position. There's no fourth option that fits natural comet behavior. Here's something that will make you think. There is exactly one documented case of cometary material flowing toward the Sun against solar wind pressure for an extended period. One confirmed example where material ejected from a comet maintained a sunward trajectory and didn't get blown back. Comet 9P/Tempel 1. On July 4, 2005, NASA's Deep Impact mission slammed a 370-kilogram copper impactor into this comet's nucleus at 10.2 kilometers per second. The collision excavated material from beneath the surface and created a plume that erupted outward from the impact site. For several hours after the impact, material from that plume maintained trajectories that defied solar wind. Some of it flowed sunward. The impact provided enough kinetic energy to launch debris with velocities that overcame solar wind pressure, at least temporarily. This is the example that comes up when you ask astronomers about anti-solar jets, the one case where we know material flowed toward the Sun, and it was created by technology, by a spacecraft deliberately smashing into the nucleus and imparting massive amounts of energy to excavated material. That should tell you something about what's required to make material flow sunward against solar wind. It takes deliberate application of force. It takes energy input beyond what natural sublimation provides. It takes, in the one confirmed case we have, technology. Now, I'm not saying Atlas was hit by a spacecraft. I'm saying that the physics of making material flow toward the Sun are well understood, and they require force. Natural outgassing doesn't provide that force. The one time we've seen anti-solar flow that lasted more than a brief moment, we created it deliberately with an impactor, and yet Atlas is producing sustained anti-solar flow without any impact event, without any observed source for the enormous energy that would be required, just doing it, continuously, for months. At this point, you might be asking the question I get all the time. If this is so strange, if Atlas is displaying behavior that violates basic cometary physics, why isn't NASA screaming about it? Why aren't astronomers publishing papers calling this the most anomalous object ever observed? Why does the media keep calling it a comet and moving on? The answer might be simpler than you think, and it's rooted in a tragedy from 1997. Comet Hale-Bopp was magnificent. At 60 kilometers in diameter, it was one of the largest comets to pass through the inner solar system during modern times. Visible to the naked eye for months, it put on a spectacular show for anyone in the northern hemisphere who bothered to look up. I saw it myself during a sailing trip. The memory is burned into my mind. This brilliant apparition hanging in the sky, multiple tails visible even from a light-polluted harbour. It was one of those rare astronomical events that captured public attention. People who'd never cared about space were suddenly asking questions, pointing at the sky, marvelling at this visitor from the outer solar system. But Hale-Bopp killed 39 people. Not the comet itself, obviously, or the Heaven's Gate cult. They convinced themselves that a spacecraft was following in Hale-Bopp's wake, hidden in the comet's tail. They believed this spacecraft would take their souls to the next level if they shed their containers, their physical bodies. So they did. 39 people in matching outfits lying in their bunks, dead from a mixture of phenobarbital and vodka. The trigger was astronomical. A comet. The publicity around a spectacular celestial visitor the speculation about what might be accompanying it. Now imagine you're at NASA in 2025. An interstellar object enters the solar system. It's displaying behavior that you cannot explain using conventional comet physics. The geometry is wrong. The tail points the wrong direction. The response to solar wind makes no sense. Do you go public with "we have no idea what this is"? Do you admit that it's behaving in ways that might suggest non-natural processes? Do you use language that could be interpreted as "this might be artificial"? Or do you call it a comet, emphasize that it's probably natural, and wait until you have enough data to make a definitive statement? Do you avoid creating panic, avoid inspiring copycat cults, avoid triggering people who might hurt themselves or others because they think aliens are coming? The answer seems obvious. You downplay the anomalies. You use reassuring language. You say comet, even if the evidence is ambiguous. You wait until the object has passed through the solar system, until it's safely distant and no longer approaching Earth, until there's zero chance of someone doing something stupid based on fear or religious fervour. Then, maybe you release the real analysis. You publish the papers acknowledging the unexplained features. You admit that this object didn't match our understanding of cometary behaviour, but you do it when there's no danger, when there's no risk of triggering another Heaven's Gate. I'm not claiming conspiracy. I'm claiming caution. Caution born from watching what happened the last time a spectacular comet captured public imagination. Caution rooted in the knowledge that space agencies have responsibilities beyond just sharing data. They have to consider public safety, societal impact, the possibility that their words might inspire dangerous behaviour. And if I'm right about this, we won't get the full story about Atlas until it's far beyond Jupiter, far from Earth, no longer a source of immediate concern. At that point, the scientific papers will come out. The detailed analyses will be published. The anomalies will be acknowledged in academic language. But by then, most people will have forgotten. The moment will have passed, and the unusual visitor that defied our understanding of comets will be a footnote in journals that the general public never reads. Let me be crystal clear about something. I'm not telling you that Atlas is definitely artificial. I'm not claiming it's an alien probe or a spacecraft or anything that requires invoking extraterrestrial intelligence. What I'm telling you is that calling it a comet is premature at best and actively misleading at worst. Here's what we know for certain. Atlas has an anti-tail pointing toward the Sun that persists across multiple observation sessions and shows no sign of being affected by solar wind or radiation pressure. Atlas has additional jets that maintain straight-line geometry despite the nucleus rotating 3 times per day. Atlas lacks the conventional dust and ion tails that should be present if natural outgassing is active enough to create the observed structures. Atlas maintained consistent anti-tail orientation before and after perihelion, despite the orbital geometry changing the sun-pole relationship. These are not interpretations. These are observations. You can see them in the images. You can verify them against cometary physics. You can compare Atlas to known comets and see the differences yourself. The question isn't whether Atlas is anomalous. It clearly is. The question is what category of anomalous object it represents. Maybe it's a natural object with composition or structure we've never encountered before. Maybe it's a chunk of another solar system with properties that Earth-based comets don't share. Maybe there's some exotic outgassing mechanism we haven't discovered that can explain the anti-tail and the geometric precision. Or maybe it's something else. Something that uses propulsion rather than relying on natural sublimation. Something that maintains orientation through active stabilization rather than chaotic tumbling. Something that exhibits geometric precision because it was designed to. I don't know which answer is correct. But I do know that calling this object a comet without addressing these anomalies is intellectual dishonesty. It's taking the comfortable label and applying it to something that doesn't fit simply because the uncomfortable alternatives are harder to discuss publicly. And that's what frustrates me. Not that people disagree about what Atlas might be. Disagreement is fine. Science thrives on competing hypotheses. What frustrates me is the refusal to acknowledge that the standard explanation doesn't work. That it's just a weird comet ignores observable facts about how this object behaves. If you've watched this far, you've seen the comparisons. You've looked at real comets obeying solar wind. You've seen Atlas ignoring it. You've examined the geometry that doesn't match rotation. You've considered the perihelion orientation problem. Now ask yourself, does the comet explanation actually fit? Does it address the anomalies? Or are you accepting it because it's the comfortable answer, the one that doesn't require rethinking assumptions? I'm not asking you to believe anything extraordinary. I'm asking you to look at the evidence without preconceptions and acknowledge that we're seeing something we don't fully understand. Because here's the reality. Whatever Atlas is, it's teaching us that our categories might not be complete, that the dividing line between natural and artificial might not be as clear as we think when we're dealing with objects from other star systems, that the universe might contain phenomena we haven't accounted for in our neat taxonomies of comets and asteroids and spacecraft. And if that makes you uncomfortable, good. Discomfort means you're engaging with the question honestly instead of reaching for easy answers. So what happens now? Atlas is past perihelion, heading back out into the outer solar system. As it retreats, it will fade from visibility. Within months, it will be too dim for most telescopes to track. Within a year or two, it will be beyond the reach of even our most powerful instruments. The window for gathering data is closing, and that's why the current silence is so critical. If there were ever a time to deploy additional observations to point every available telescope at this object and document its behavior in exhaustive detail, this is it. Are those observations happening? Probably. But we're not seeing the results published in real time. We're getting brief updates, sanitized statements, reassurances that everything is normal. Maybe everything is normal. Maybe the detailed analyses will come out next year and show that all the anomalies have conventional explanations. Maybe Atlas will turn out to be exactly what they're calling it, just a weird comet from interstellar space that happens to have unusual properties. But maybe not. Maybe the analyses will show something unprecedented. Maybe the data, when fully examined without the pressure of real-time public scrutiny, will reveal behaviors that cannot be explained by natural processes. And if that happens, if the scientific papers eventually acknowledge that Atlas was genuinely anomalous in ways that challenge our understanding, will anyone care by then? Will anyone remember the object that briefly graced our sky with its mysterious presence? Or will it be forgotten, dismissed as old news, ignored by a public that's moved on to newer mysteries? That's the tragedy of how we handle these situations. By the time we get honest acknowledgement of the anomalies, the moment has passed. The public attention has shifted elsewhere. The opportunity for collective wonder and curiosity has evaporated. And maybe that's intentional. Maybe that's exactly how institutions want it. Let the object fade, let public interest wane, then release the truth to academic circles where it can be discussed without causing panic or inspiring dangerous behavior. It's a rational strategy. It's a safe strategy. But it's also a strategy that treats the public like children who can't be trusted with ambiguous information. And I'm not sure that's justified. This video isn't about convincing you that Atlas is artificial. It's not about pushing any particular explanation for the anomalies. It's about asking you to look at the evidence directly. To compare this object to known comets. To see the differences with your own eyes instead of accepting reassurances from authorities who might have reasons to downplay the strangeness. If you walk away from this video still believing Atlas is a normal comet, fine. But I hope you walk away having at least questioned that belief, having asked yourself whether the standard explanation truly accounts for what we're observing. Because the alternative, accepting explanations without examining evidence, is how we miss the most interesting discoveries. It's how we let phenomena that could revolutionize our understanding slip past unexamined. Atlas might be a comet, but it might be something we don't have a category for yet. Something that exists in the grey zone between natural and artificial, between familiar and unprecedented, between comfortable and challenging, and acknowledging that uncertainty, sitting with that discomfort, is how science actually advances, not by rushing to familiar answers, but by honestly grappling with observations that don't fit our models. So here's my challenge to you. Don't take my word for anything. Don't take NASA's word. Look at the images yourself. Compare Atlas to comets. Examine the physics of solar-wind interaction. Consider the geometry problems. Think about what it would take to create the behaviors we're observing. Then, form your own conclusion, not based on what authorities tell you, not based on what sounds reasonable, but based on evidence. That's all I'm asking. Look at the data, think critically, and don't be afraid to admit when something doesn't add up. If this analysis has made you think, if it's raised questions you want to explore further, hit that subscribe button. We're going to keep following Atlas as long as it's visible, and we're going to keep examining the data honestly, regardless of where it leads. Drop a comment telling me your thoughts. Do the anomalies concern you? Do you have alternative explanations that address the geometry and solar wind problems? Have you been following this object since discovery, or is this your first deep dive into its strange behavior? I want to hear from you. Because this isn't about one person's opinion. This is about a community of people who care about evidence, who value critical thinking, who aren't satisfied with pat answers to complex questions. And if you want to support more investigations like this, there's a Patreon link in the description. We're trying to cover the Artemis II launch next month, and bringing proper equipment and crew to document that historic mission costs money. Every dollar helps, and more importantly, every dollar sends a message that you value honest examination of evidence over comfortable narratives. Thank you for watching, thank you for thinking critically, and thank you for being willing to sit with uncertainty instead of rushing to comfortable conclusions. Whatever Atlas is, it's teaching us something important. Maybe about comets, maybe about interstellar objects, maybe about the limits of our current understanding, and that's valuable, regardless of whether the object turns out to be natural or something stranger. Until next time, keep looking up, keep questioning, and keep demanding evidence instead of accepting reassurance. The images keep coming back to haunt me. Every time I think I've found a conventional explanation, every time I tell myself, it's just an unusual comet from another star system, I pull up another comparison and the explanation falls apart. Look at this sequence. Comet McNaught 2007, one of the brightest comets of the 21st century, visible in broad daylight at its peak. Multiple tail structures, complex coma morphology, spectacular dust fans, and every single feature obeying the fundamental rule: material flows away from the sun. The ion tail, narrow and straight, points precisely anti-solar. The dust tails, broader and curved, sweep backward following the pressure gradient. Even the strange striations in the dust, probably created by rotating jets on the nucleus, all bend away from the solar direction. Now Atlas. Same type of enhanced imaging, same processing techniques designed to reveal subtle structure, and the material just doesn't care about the sun. The anti-tail maintains its sunward orientation. The auxiliary jets spread at geometric angles that have nothing to do with solar wind direction. There's no bending, no curving, no evidence that the most powerful force in the inner solar system is having any effect whatsoever. I keep asking myself what mechanism could explain this. What natural process creates streams of material that ignore solar radiation pressure? And I keep coming back to the same answer. There isn't one. Not in our current understanding of cometary physics. Some researchers have suggested magnetic fields. Maybe Atlas has an unusually strong internal magnetic field that channels ionized gas along field lines, creating jets that don't respond normally to solar wind. It's creative. It's trying to work within known physics, but it falls apart under scrutiny. First, comets don't generate significant magnetic fields. They're not large enough. They don't have the internal structure. A comet nucleus is basically a rubble pile. Ice, rock, dust, all loosely bound together by weak gravity. There's no mechanism for generating the kind of organized magnetic field that would be needed to channel material against solar wind pressure. Second, even if you somehow had a magnetic field, it would interact with the solar wind's magnetic field. The solar wind isn't just particles, it's magnetized plasma. When the sun's magnetic field encounters a planetary magnetosphere, you get complex interactions, reconnection events, bow shocks. A comet-scale magnetic field wouldn't create neat, straight jets. It would create turbulent, chaotic structures where the fields interact and compete. Third, magnetic fields only affect ionized material. If the anti-tail is made of neutral dust particles, as the large particle theory suggests, then magnetic fields are irrelevant. The material would still respond to radiation pressure. You can't have it both ways. Either it's ionized gas affected by magnetic fields, in which case it should show the characteristic behaviors of ion tails, or it's neutral dust, in which case magnetic fields don't help explain the anomaly. The magnetic field hypothesis is what scientists do when they're trying very hard to avoid an uncomfortable conclusion. They're reaching for exotic explanations that technically don't violate known physics, but require conditions we've never observed in similar objects. It's the anything but artificial approach. Let me show you something else that doesn't add up. Comet Ikeya-Jang, 2002. This object has a 367-year orbital period, meaning it's passed through the inner solar system dozens of times over recorded history. Chinese astronomers documented it in 1661. It came back in 2002, giving modern instruments their first good look. Ikeya-Jang showed textbook comet behavior. As it approached the sun, its activity increased. Outgassing intensified. The coma expanded. Tails developed and grew longer. All of this matches what we understand about comets. Sunlight heats the nucleus, ice is sublimate, material escapes, solar wind shapes it into tails. But here's the interesting part. Ikea Jang's activity wasn't constant. It showed bursts and lulls. Some days the coma would brighten suddenly as a fresh patch of ice got exposed to sunlight. Other days activity would decrease as that patch got covered by dust or rotated out of direct sun. The jets would turn on and off as different vents faced the sun during the nucleus's rotation. This is what natural outgassing looks like. Variable, responsive to solar heating, dependent on which parts of the surface are illuminated, chaotic and irregular because comet nuclei are irregular objects with heterogeneous surfaces. Atlas doesn't show this variability. The antitail persists with remarkable consistency. The geometric configuration of the jets remains stable across observation sessions separated by weeks. There's no evidence of the kind of activity burst you'd expect from a rotating, irregularly shaped nucleus with scattered ice deposits. It's behaving more like something with a controlled, sustained output than something responding passively to solar heating. The difference is subtle but important. Natural outgassing flickers. It surges and fades. It creates structures that evolve and change as surface conditions change. Atlas's structures are stable, almost engineered in their consistency. And before you say, maybe it's just a very uniform nucleus, think about what that would require. You'd need a perfectly homogeneous distribution of ices across the surface. You'd need every active region to have identical composition and identical sublimation rates. You'd need the surface geometry to be regular enough that rotation doesn't create the usual pattern of varying solar illumination. We've never seen a comet nucleus like that. Every comet we've imaged up close, Halley, Borrelly, Wild 2, Tempel 1, Hartley 2, Churyumov-Gerasimenko, shows irregular heterogeneous surfaces, rough terrain, localized active regions, dramatic differences between illuminated and shadowed areas. The idea that Atlas just happens to be perfectly uniform, that it just happens to have properties that create stable, geometric outgassing patterns, is statistically implausible. You're invoking a special case to explain away the anomalies, rather than considering that maybe the anomalies are telling us something important. Here's another comparison that troubles me. Comet 17P/Holmes, 2007. This object did something spectacular. It suddenly brightened by a factor of nearly 1 million, going from invisible to the naked eye to one of the brightest comets in the sky in the span of about 42 hours. The outburst created a massive spherical coma that expanded at visible speed, eventually growing larger than the Sun in angular size. We still don't fully understand what caused Holmes's outburst. Maybe a landslide on the nucleus exposed fresh ice. Maybe a cavity full of volatile materials breached to the surface. Maybe a subsurface pressure buildup triggered an explosive release. The mechanism remains debated, but here's what we do know. The material ejected during the outburst behaved exactly as physics predicts. Gas and dust expanded spherically from the nucleus, initially moving outward in all directions. Then solar wind took over. The expanding sphere became asymmetric as the solar-facing side got pushed back. Within days, a conventional tail began forming as radiation pressure shaped the dust into the familiar swept-back structure. Even during a violent, explosive event that released enormous amounts of material in all directions, solar wind ultimately dominated. The physics won. The material that started out moving sunward got slowed, stopped, and pushed backward. Atlas doesn't show this. Its anti-tail isn't a brief burst of material that temporarily resists solar wind before physics takes over. It's a sustained structure that persists for months, showing no sign of solar wind gradually winning the battle. What process maintains that? What keeps feeding material into the anti-tail with enough velocity to continuously overcome solar wind pressure? Natural outgassing should exhaust itself. As surface ice sublimates, it either runs out or gets buried under an insulating layer of dust. You can't maintain high-rate outgassing indefinitely without depleting your volatile inventory. Unless there's a mechanism for replenishing the volatiles or for generating the outflow through something other than thermal sublimation. And I can't think of a natural mechanism that fits. The numbers don't work either. Let's do some rough calculations. Solar wind pressure at Earth's orbit is about 2 nanopascals. Radiation pressure adds maybe another nanopascal for typical comet dust particles. That doesn't sound like much, but integrated over time and area, it's significant. To overcome 3 nanopascals of pressure, you need to eject material at specific velocities depending on particle size. For micron-sized dust, you'd need ejection velocities of several hundred meters per second to keep the material from being pushed back. For larger particles, the required velocities are lower, but you still need sustained force to counteract the cumulative effect of radiation pressure. Normal cometary outgassing produces velocities around 100 to 500 meters per second, depending on the volatile composition and surface temperature. That's in the ballpark for creating jets that initially resist solar wind, which is why freshly ejected material can travel some distance from the nucleus before getting swept back. But maintaining anti-solar flow for hundreds of thousands of kilometers, the material would need to be continuously accelerated, or it would need initial velocities far exceeding what thermal sublimation can provide. Sublimation is a gentle process. Molecules escape when they gain enough thermal energy to break free of the solid surface. It doesn't create high-velocity jets the way, say, a pressurized gas escaping through a nozzle would. You could maybe get higher velocities if you had subsurface cavities, where pressure builds up before breaching to the surface. The gas would accelerate through the breach, potentially reaching higher speeds than simple surface sublimation. But that's a transient event. Once the pressure releases, the high-velocity flow stops. You can't maintain it continuously. Atlas maintains it continuously. I want to show you one more comparison, and this one is particularly relevant because it's the other confirmed interstellar object we've studied in any detail. Comet 2I/Borisov, discovered in August 2019, was the first interstellar comet identified before it reached perihelion, giving us time to study it throughout its passage. Borisov looked like a comet, not just in the general sense, but in specific, measurable ways. Its composition matched solar system comets. The ratio of dust to gas was typical. The colour and reflectivity were normal. The outgassing rate fit standard models. Even the carbon monoxide and water abundances were within the expected range. More importantly, Borisov's tails behaved normally. The dust tail swept back from the sun. The coma expanded and contracted in response to solar heating. Jets appeared and evolved as the nucleus rotated. Every observation confirmed that Borisov, despite coming from another star system, was functionally identical to our native comets. This makes sense if comets form through similar processes regardless of which star they orbit. The physics of ice and dust accumulation in protoplanetary disks should be universal. A comet from another system might have slightly different composition, depending on that system's specific chemistry, but the basic architecture should be the same. Borisov proved this. Interstellar comet. Familiar behavior. The origin doesn't matter if the object type is the same. So why doesn't Atlas behave like Borisov? If they're both interstellar comets, both formed in distant planetary systems and ejected into the void, why does one act exactly like our comets, while the other violates basic cometary physics? The standard answer is that Atlas is just more unusual than Borisov. Maybe it formed under different conditions. Maybe it has exotic composition. Maybe it's showing us the range of natural variation in interstellar comets. But that answer assumes the conclusion. It assumes both objects are natural comets, and then works backward to explain why they're different. What if the difference is more fundamental? What if one is a comet and the other is something else? I can already hear the objections. You're making extraordinary claims without extraordinary evidence. And that's fair. I'm not claiming I have definitive proof that Atlas is artificial. I'm not saying I can demonstrate beyond doubt that it's technology rather than nature. What I'm saying is that the evidence we have doesn't fit the comet category, as well as people keep claiming. That calling something a comet when it violates the basic physics of how comets behave is misleading at best. Science is supposed to follow evidence to conclusions, not start with acceptable conclusions and force evidence to fit. And right now I see a lot of forcing, a lot of inventing special cases and exotic conditions to preserve the "it's definitely a comet" narrative. Why? What makes that narrative so important to protect? Part of it is professional conservatism. Scientists are trained to favour conventional explanations and to be sceptical of anything that smells like sensationalism. That's good practice most of the time. It prevents us from jumping to wild conclusions based on insufficient data. But sometimes it goes too far. Sometimes the desire to avoid looking foolish, to avoid being associated with fringe ideas, becomes an impediment to honest evaluation of evidence. You'd rather invent an unlikely natural explanation than consider that maybe, just maybe, we're seeing something that doesn't fit our existing categories. And there's another factor. The taboo around discussing potential artificial origins for astronomical objects. Say those words, artificial origin, and you've immediately associated yourself with UFO enthusiasts and conspiracy theorists. You've left the realm of respectable science and entered the domain of speculation and pseudoscience. Never mind that SETI is a legitimate scientific field that operates on the premise that technological civilizations might exist elsewhere. Never mind that we've sent our own probes into interstellar space. Never mind that the basic physics of interstellar travel doesn't violate anything we know. The moment you suggest an observed object might be artificial rather than natural, you've crossed a line. This taboo serves a purpose. It prevents scientists from wasting time on every ambiguous observation, from seeing aliens under every rock. But it also creates a blind spot. It makes certain hypotheses unthinkable, even when evidence might point in that direction. I'm not saying Atlas is definitely artificial. I'm saying the hypothesis shouldn't be reflexively dismissed. It should be evaluated on evidence like any other hypothesis. And if the evidence keeps showing behaviours inconsistent with natural comets, then maybe we need to at least consider alternative explanations, instead of inventing increasingly elaborate scenarios to force the data into the comet framework. The rotation axis problem alone should be raising more eyebrows than it is. The fact that the anti-tail maintained its orientation through perihelion, despite the geometric constraints, is extraordinary. It requires either absurd coincidence or an active mechanism maintaining orientation. But I haven't seen any papers seriously addressing this. The few analyses that mention it hand-wave it away with vague references to possible axis precession or alternative vent locations. Nobody's doing the detailed modelling to show how natural processes could produce the observed stability. Why not? Is it because the modelling would reveal that natural explanations don't actually work? Is it because seriously investigating the anomaly might lead to conclusions that are professionally uncomfortable? I don't know, but the silence bothers me. These aren't minor discrepancies that can be ignored. These are fundamental violations of how we understand comets to behave. They deserve rigorous analysis, detailed modelling, and honest acknowledgement of what the data is showing. Instead, we get reassuring statements. It's a comet. It's unusual but not unprecedented. There are natural explanations for the features we're seeing. And then the analysis stops. The hard questions don't get asked. The anomalies get filed away as curiosities rather than investigated as genuine mysteries. Maybe I'm wrong. Maybe detailed analyses are happening behind the scenes, and we'll see comprehensive papers next year that explain everything. Maybe there are natural mechanisms I'm not aware of that perfectly account for Atlas's behaviour. But until I see those analyses, until someone shows me the detailed physics of how natural outgassing creates anti-solar tails that persist for months, how rotation doesn't affect jets that should be rotating, how orientation remains stable through perihelion, until someone addresses these problems with actual physics rather than hand-waving, I remain skeptical of the "it's definitely just a weird comet" narrative. Look at the images one more time. Comet after comet, dozens of examples spanning decades of observations, all showing the same fundamental behaviour. Material flows away from the sun, jets fan out with rotation, activity varies with solar heating, the physics is consistent, the patterns are predictable. Then Atlas, different. Anomalous in multiple independent ways, behaving like something that doesn't fit the pattern. Maybe it's revealing a gap in our knowledge of cometary physics. Maybe it's showing us that natural processes can create configurations we haven't encountered before. Maybe it's expanding our understanding of what's possible. Or maybe it's not a comet at all. Maybe it's something else, something we don't have a neat category for, something that requires us to think beyond the comfortable binaries of natural versus artificial, familiar versus unprecedented. I don't claim to know which answer is correct, but I do claim that the question deserves better than dismissive reassurances and forced explanations. It deserves rigorous investigation and honest acknowledgement of what the data actually shows. Because whatever Atlas is, it's teaching us something. About comets, about interstellar objects, about our willingness to confront evidence that doesn't fit our expectations. And that lesson is valuable regardless of whether the object turns out to be natural or something stranger. The enhanced images keep revealing more details. Different wavelengths, different processing techniques, all showing the same fundamental strangeness. In infrared, the anti-tail glows with thermal emission that suggests particulate material rather than pure gas. In visible light, the geometric precision of the jet structure is even clearer. In ultraviolet, the lack of typical cometary emission lines raises questions about composition. Every new observation adds data, and every new piece of data makes the standard comet explanation fit worse, not better. We're not converging on understanding, we're diverging into deeper mystery, and the clock is ticking. Atlas is fading. Soon it will be beyond the reach of detailed observation. The window for gathering high-quality data is measured in weeks now, not months. Whatever questions we don't ask now, whatever observations we don't make, we might never get another chance. This is the frustration I feel watching this unfold. We have an object displaying genuinely anomalous behaviour, and instead of mounting a comprehensive observational campaign to document every possible aspect of it, we're getting sporadic observations and reassuring statements that everything is normal. It's not normal, the data shows it's not normal, and pretending otherwise doesn't serve science or public understanding. It serves institutional comfort and the desire to avoid difficult conversations. But difficult conversations are where discovery happens, where we learn things that challenge our assumptions and expand our knowledge. And avoiding those conversations, because they might lead to uncomfortable conclusions, is how we miss the most important findings. So I'll keep looking at the data, keep comparing Atlas to known comets, keep asking the questions that the official analyses seem reluctant to address. Not because I'm trying to prove a specific conclusion, but because the evidence deserves honest examination. And if that makes me a nuisance, if it associates me with fringe theories and speculative thinking, so be it. I'd rather be wrong while asking real questions than right while accepting comfortable lies. The images don't lie, the physics doesn't lie, and anyone willing to look at both honestly can see that something about this object doesn't add up. What the something is, I can't say with certainty, but I can say with absolute confidence that calling it a normal comet and moving on is intellectual dishonesty. The anomalies are real, the questions are legitimate, and they deserve better answers than we're getting. 3 months ago, I didn't know what a Larsen-Sekanina filter was. Now I can't stop running images through it, because every time I do, the differences between Atlas and real comets become more stark, more undeniable, more impossible to dismiss with vague explanations about unusual composition or exotic outgassing. The filter works by subtracting rotationally averaged images from the original, effectively removing the symmetric coma and revealing the fine structure of jets and tails. It's a standard technique in cometary analysis, used for decades to study how material flows from comet nuclei. You can download the software. You can process the images yourself. This isn't hidden data or classified observations. It's publicly available information that anyone can examine, so I've been examining it. And what I see keeps me up at night. Here's Comet Hyakutake, 1996. Remarkable object, passed extremely close to Earth, gave us unprecedented views of cometary structure. The Larsen-Sekanina processed images show exactly what you'd expect. Jets emanating from discrete source regions on the nucleus, fanning out as rotation carries each vent across the field of view, all of the material eventually curving backward under solar wind pressure. You can trace individual streamlines in the processed images, follow them back from the tail to their source points on the nucleus, watch how they curve and evolve. See where different jets merge into the broader tail structure. It's beautiful, actually. The physics playing out in real time, visible in these processed observations. The jets aren't straight. They can't be straight because the nucleus is rotating and solar wind is pushing. Each jet is a spiral, a curved path traced by material escaping a vent that's spinning through space, while external forces act on it. The mathematics of the trajectories match exactly what you'd predict from the rotation period, solar wind speed, and particle size distribution. This is what natural cometary jets look like when you filter out the noise and examine the structure carefully. Curved, evolving, responding to every force acting on them. Now run Atlas through the same filter, same technique, same software, same processing parameters. And the jets are straight. The anti-tail is straight. The auxiliary structures are straight. There's no spiral pattern, no evidence of rotation affecting the outflow, no curving under solar wind pressure. It's as if the material is being emitted along fixed vectors that maintain their orientation regardless of the nucleus's rotation or the external forces acting on them, which shouldn't be possible for passive outgassing. I've tried to find counterexamples. I've searched through decades of cometary observations looking for any object that shows similar straight-line jet structure while rotating. I can't find one. Every active comet shows the characteristic spiral pattern when you process the images to reveal fine structure, except Atlas. Someone suggested to me that maybe the processing technique doesn't work correctly for interstellar objects. Maybe the different composition or the extreme distance throws off the filter somehow, creating a apparent straight line structure that's actually an artifact of the processing. So I tested it, took the Borisov data and ran it through identical processing. Borisov is also interstellar, also observed at similar distances, also has potentially unusual composition. If the processing creates artifacts for interstellar objects, it should affect Borisov too. It doesn't. Borisov's processed images show normal curved jets, normal spiral structure, normal evidence of rotation, and solar-wind interaction. The processing works fine. The technique isn't creating full straight-line structures. Atlas's jets really are that geometrically precise. And I can't explain it with natural processes. Let me show you something else that's been bothering me: the dust production rate. Comets shed material constantly as they approach the Sun, and we can measure how much dust they're producing by analysing the brightness and size of the coma. More dust means brighter coma, and the relationship between brightness and dust production is well established. For typical comets, dust production increases as they get closer to the Sun, peaks around perihelion, then decreases as they move away. The curve is smooth and predictable because it's directly tied to solar heating. More sunlight means more sublimation means more dust. Atlas showed a different pattern. Its dust production didn't follow the smooth curve. Instead, it showed discrete jumps. Sudden increases in activity that weren't correlated with distance from the Sun. Then periods of stable production. Then another jump. This is unusual but not unprecedented. Some comets show outburst behavior where activity suddenly increases, possibly due to ice cliffs collapsing or subsurface cavities breaching. But those outbursts are typically followed by gradual decline, as the newly exposed ice gets covered by dust or sublimates away. Atlas's activity increases didn't decline. They stayed at the new level until the next jump. It's step function behavior rather than burst and decay, like something was being turned on rather than something being exposed and then exhausted. The timing of these jumps is interesting too. They didn't correlate with perihelion or with any obvious orbital milestone. They seemed almost random. Or not random, but following a schedule that has nothing to do with solar heating. I'm probably reading too much into this. Comets are complex objects, and activity patterns can be influenced by factors we don't fully understand. Rotation could expose different surface regions with different ice concentrations. Internal structure could create delayed responses to solar heating. There are plausible natural explanations for irregular activity. But combined with everything else, combined with the straight jets, and the persistent anti-tail, and the geometric precision, and the orientation stability through perihelion, it's another data point that doesn't quite fit the pattern we expect from natural outgassing. The spectroscopic data raises questions too. Early observations showed that Atlas's coma was dominated by carbon dioxide, which is unusual. Most comets are water-rich. CO2 is present, sure, but it's typically a minor component compared to H2O. The explanation given was that Atlas formed in an extremely cold environment, possibly around a different type of star, where water stayed frozen deeper while CO2 remained near the surface. Plausible. Interstellar comets should show compositional diversity reflecting their diverse origins. But as Atlas approached perihelion and surface temperatures increased, the water should have started sublimating too. We should have seen the CO2 to H2O ratio change as the thermal wave penetrated deeper into the nucleus. That's what happens with our comets. Composition evolves as different volatiles with different sublimation temperatures get activated at different solar distances. Atlas's composition stayed remarkably stable. The CO2 dominance persisted even when the nucleus should have been hot enough to sublimate significant water ice. Either the nucleus is pure CO2 ice with almost no water, which is extremely unusual, or there's something else going on. Pure CO2 composition creates its own problems. CO2 ice is more volatile than water ice. It sublimates at lower temperatures. If the nucleus is mostly CO2, it should have been outgassing strongly even when it was far from the Sun, back when it was first discovered beyond Jupiter's orbit. But the early observations showed relatively low activity. Atlas brightened significantly, only as it approached the inner solar system. That's backward from what you'd expect for a CO2-rich nucleus. It should have been most active in the outer solar system where CO2 sublimates readily, then should have decreased in activity in the inner system where the CO2 gets depleted. Instead, it did the opposite. unless the composition isn't really CO2 dominated, unless the spectroscopic signatures we're interpreting as CO2 are actually something else, something with similar emission lines but different origin. I'm not a spectroscopist. I don't have the expertise to reinterpret the spectral data. But I know enough to recognize when observations don't match expectations, and the composition story doesn't match what we understand about volatile sublimation. There's also the brightness problem. Atlas got bright, really bright. At peak, it was visible in amateur telescopes from dark sky locations, remarkable for an object at that distance. The brightness implied a large active surface area producing substantial dust. But the nucleus size estimates suggest Atlas is small, maybe a few kilometers across. That's not tiny, but it's not enormous either. To produce the observed brightness from that size nucleus, you need either very efficient dust production or very high reflectivity. Very efficient dust production means vigorous outgassing, which brings us back to all the questions about how the jets maintain their geometry and orientation. Very high reflectivity means the surface is covered in fresh, bright ice, which contradicts the idea that we're seeing deep subsurface CO2 from a cold formation environment. The numbers don't quite add up. The brightness is higher than the size and activity should produce, unless something about Atlas is unusual. Maybe the dust particles are particularly reflective. Maybe the size estimate is wrong. Maybe the coma is trapping and re-emitting light in unexpected ways. Or maybe there's a component to the brightness that has nothing to do with reflected sunlight. Maybe there's some emission mechanism we're not accounting for. I don't know what that would be, but I know that the simple calculation of reflected solar radiation doesn't fully explain what we're seeing. Amateur astronomers have been contributing observations too, and their images show details that sometimes get overlooked in professional analyses. When you have hundreds of amateur telescopes pointed at the same object from different locations, you get temporal coverage that single professional instruments can't match. And what the amateurs have been documenting is variability. Not the smooth, predictable variability of rotating jets, but irregular changes in brightness and structure that don't correlate with rotation period. The anti-tail doesn't pulse with an 8-hour period as you'd expect if it were tied to rotation. Instead, it shows fluctuations on timescales of hours to days with no obvious pattern. This could be observational noise. Amateur images vary in quality, and atmospheric conditions can create apparent brightness changes that aren't real. But when multiple independent observers in different locations report similar variations at similar times, it becomes harder to dismiss as artifacts. What could cause irregular variations in tail brightness? Changes in dust production rate, maybe. But we're back to the same question. What controls the production rate if it's not solar heating and rotation? Natural outgassing should be relatively stable over short timescales unless you're getting discrete outburst events. An outburst should show characteristic light curves, brightening rapidly, then fading gradually. Atlas's variations don't match that pattern. The more I look at the data, the more I feel like I'm staring at a jigsaw puzzle where the pieces almost fit but not quite. Each observation can be explained individually with some creative interpretation, but when you try to assemble them into a coherent picture of a natural comet, the pieces don't lock together properly. There are gaps, there are contradictions, there are places where you have to force things to make them fit, and every time I point this out, every time I say this doesn't quite make sense, the response is comets are complex, or we don't fully understand interstellar objects, or there are natural processes that could explain this, all of which is true. Comets are complex. We don't fully understand interstellar objects. There probably are natural processes we haven't discovered yet. But that's not the same as demonstrating that those unknown natural processes actually explain Atlas. You can't just invoke, we don't know everything, as a universal explanation for anomalies. At some point you have to acknowledge that the standard model isn't fitting, and maybe we need to consider alternatives. The resistance to considering alternatives is what frustrates me most. Not the disagreement about what Atlas is. Disagreement is healthy, and science advances through competing ideas tested against evidence. What frustrates me is the refusal to even entertain certain possibilities as worth investigating. Suggest that Atlas might not be a comet, that it might be something else, and the response isn't interesting idea, let's examine the evidence. The response is, that's extraordinary, we need extraordinary evidence, and what we have isn't extraordinary enough. But what counts as extraordinary evidence? We have an object violating basic cometry physics in multiple independent ways. We have geometric precision that natural outgassing shouldn't produce. We have stability through perihelion that requires either absurd coincidence or active orientation control. We have composition and brightness and variability that don't quite match expectations. How much anomalous behavior does an object need to show before we admit that maybe our initial categorization was wrong? How many ways does it need to violate our models before we consider that perhaps it doesn't fit the category we've assigned it to? I think the threshold for extraordinary evidence keeps moving precisely because the alternative explanation is uncomfortable. If Atlas isn't a comet, what is it? And if we start seriously considering that question, where does it lead? That's the real issue, not the evidence itself, but the implications of taking the evidence seriously. Because if Atlas is something other than a natural comet, if it's showing signs of non-natural behavior, then we're confronting possibilities that astronomy as a field isn't ready to deal with publicly. The institutional memory of Hale-Bopp isn't just about cult tragedy. It's about what happens when astronomical observations get interpreted in ways that inspire fear or irrational behavior. And the lesson learned wasn't communicate more clearly. The lesson learned was be very careful what you say publicly about unusual objects, which creates a dilemma. How do you honestly discuss anomalous observations without triggering public panic? How do you maintain scientific integrity while also being responsible about communication? The answer seems to be, you categorize the object safely, you emphasize natural explanations, and you downplay the anomalies until you're absolutely certain what you're dealing with. And if certainty never arrives because the object fades from view before you can gather definitive data, well, at least you didn't cause another Heaven's Gate. I understand that calculus. I don't entirely agree with it, but I understand it. The problem is it leaves people like me, people who are looking at the data and seeing genuine mysteries, feeling gaslit. We're told everything is normal when the observations clearly show it's not normal. We're told to trust the experts when the experts seem more interested in reassuring the public than in honestly grappling with the anomalies, and that breeds exactly the kind of conspiracy thinking that institutions are trying to avoid. When people see obvious anomalies being dismissed with hand-waving explanations, they don't conclude that the experts know something they don't. They conclude that the experts are hiding something. Maybe they are hiding something, not maliciously, not as part of some grand conspiracy, but out of an abundance of caution born from past experience, hiding it behind technical language and qualified statements and reassurances that there are natural explanations, even if we haven't fully worked them out yet. The truth might be simpler and more concerning. They don't know what Atlas is. The data doesn't fit their models. But they can't say that publicly, because admitting uncertainty about an object passing through the inner solar system could create exactly the kind of panic they're trying to avoid. So they call it a comet. They emphasize the familiar aspects and downplay the anomalies. They wait for it to leave, for public attention to shift elsewhere, for the moment of potential crisis to pass safely. Then, maybe in a few years, the honest papers will come out. The ones that acknowledge the anomalies, that admit the standard comet model doesn't fully explain the observations, that suggest alternative mechanisms without committing to specific explanations, and by then, nobody will care. The object will be gone, the media will have moved on, the public will have forgotten, and the scientific literature will record the truth in language so technical and hedged that only specialists will read it or understand its implications. That's the pattern I keep seeing in how unusual astronomical objects get handled. Initial reassurance, cautious language, emphasis on conventional explanations. Then, after the moment passes, more honest acknowledgement of uncertainty and anomaly. It's a reasonable strategy for managing public perception, but it's a terrible strategy for advancing knowledge or maintaining public trust in scientific institutions, because people aren't stupid. They can see the images, they can compare Atlas to other comets, they can recognize when something doesn't quite fit the explanations being offered. And when they see that discrepancy, when they notice the gap between what the data shows and what the official statements say, they lose trust. Not in science, in institutions, in the official narrative, in the reassurances that everything is under control and perfectly understood. And that loss of trust is dangerous. It's what drives people toward conspiracy theories and fringe explanations. It's what makes them vulnerable to misinformation. It's what creates the environment where another Heaven's Gate becomes possible. The irony is painful. Institutions downplay anomalies to prevent panic and irrational behavior. but the downplaying itself creates the conditions that breed exactly those responses. What's the alternative? Honest communication about uncertainty, clear acknowledgement of what we know and what we don't, transparent discussion of anomalies without jumping to sensational conclusions, but also without dismissing legitimate questions. Say, this object is showing behaviours we don't fully understand. We're calling it a comet based on its general characteristics, but there are aspects of its behaviour that don't match our models. We're gathering more data to better understand what we're seeing. Here are the possibilities we're considering. Here's what we'd need to observe to distinguish between them. Would that create some anxiety? Probably. Would some people misinterpret it or draw unwarranted conclusions? Certainly. But at least it would be honest. At least it would maintain the integrity of the scientific process instead of sacrificing truth for comfort. And it would prevent situations like this, where people who are paying attention to the data feel like they're being lied to, because the official explanations don't match what the observations show. I'm not claiming I have all the answers. I'm not saying I know what Atlas is with certainty. What I'm saying is that the answers we're being given don't fit the data, and the refusal to acknowledge that disconnect is eroding trust in exactly the institutions that need to maintain credibility to communicate effectively during actual crises, because eventually there will be a real crisis, an object on a collision course, or a solar storm that threatens infrastructure, or some other astronomical event with genuine immediate danger. And when that happens, institutions will need the public to trust their assessments and follow their recommendations. If they've spent years dismissing legitimate questions and downplaying obvious anomalies, that trust won't exist. People will assume they're being managed rather than informed. They'll second-guess official statements. They'll look for alternative sources of information that might be less reliable, but at least seem more honest about uncertainty. The Boy Who Cried, Wolf works in reverse too. If you keep saying everything is fine when people can see it's not quite fine, eventually they won't believe you when you say there's danger. Atlas might end up being a nothing event. It might fade into the outer solar system, revealing nothing more than we already know, leaving us with interesting data about an unusual comet and nothing more dramatic. But the way it's being handled, the disconnect between observation and explanation, the institutional reluctance to honestly address anomalies, that matters regardless of what Atlas turns out to be. Because it's setting a precedent. It's establishing a pattern of communication that prioritizes reassurance over honesty, comfort over accuracy. And that pattern will persist even after Atlas is gone, affecting how we handle the next unusual object and the one after that. I want to believe that scientists and institutions are acting in good faith, that they're making difficult decisions about communication with the best interests of the public in mind, that the reassurances are genuine and based on knowledge I don't have access to, but the data keeps bothering me. The images keep showing things that don't fit the explanations, and the more I look, the more I feel like something important is being left unsaid. Maybe I'm wrong. Maybe there are detailed analyses happening that will be published soon, showing exactly how natural processes explain every anomaly. Maybe I'm missing something obvious that makes all the pieces fit together. But until I see those analyses, until someone shows me the physics that makes this all make sense, I can't shake the feeling that we're watching something genuinely unprecedented while being told it's routine. And that bothers me more than the mystery of what Atlas actually is. The closest comparison we have to Atlas isn't a comet at all, it's Oumuamua. And that should tell you something important about what we're actually looking at. October 2017. Pan-STARRS telescope in Hawaii picks up a fast-moving object on a hyperbolic trajectory. Within days, astronomers realized this thing came from outside our solar system. First confirmed interstellar visitor. The astronomy community goes into overdrive trying to gather observations before it fades from view. Oumuamua was strange from the start. The light curve suggested an elongated shape, maybe 10 times longer than it was wide, tumbling end over end every 7 hours or so. No visible coma, no tail, no sign of outgassing. It looked like an asteroid, not a comet. But then it did something asteroids don't do. It accelerated. As it swung past the sun and headed back out into deep space, it sped up slightly, yet moving faster than gravity alone could explain. The excess acceleration was small, maybe 0.00001 meters per second squared, but it was real and measurable. Comets accelerate all the time. Outgassing creates a rocket-like thrust as material jets from the nucleus. The effect is well documented. Every active comet shows non-gravitational acceleration to some degree. So the initial explanation for Oumuamua's acceleration was simple. It must be outgassing, even though we can't see any coma or tail. But the numbers didn't work. To produce the observed acceleration without visible outgassing, you need either extremely efficient thrust from an invisible gas, or you need the object to be very low mass, or you need some other force we're not accounting for. The invisible outgassing explanation requires the gas to be something we can't easily detect. Not water vapor, which would show up in spectroscopy. Not CO2, which would also be visible. Maybe pure nitrogen or pure hydrogen, volatiles that don't produce strong signatures in the wavelengths we were observing. Possible, but weird. Why would an interstellar object be made of pure nitrogen ice? That's not something we see in our solar system. And why would outgassing strong enough to accelerate the object not produce any visible coma? The low-mass explanation requires Oumuamua to be incredibly fluffy, porous to the point where it's more void than solid, density like styrofoam. That would reduce the mass enough that even minimal outgassing could produce measurable acceleration. Also possible. Also weird. And it contradicts the rotation rate, something that fluffy should be spinning faster, because low density means low moment of inertia. The observed rotation period suggested higher density than the low-mass explanation required. The numbers were contradicting each other. No single natural explanation could account for all the observations simultaneously. You could explain the acceleration without gassing if you assumed certain properties. But those properties contradicted the light curve. You could explain the light curve with certain shapes and densities, but those shapes and densities didn't match the rotation period. Every explanation solved one problem while creating another. Enter the artificial hypothesis. What if Oumuamua wasn't outgassing? What if the acceleration came from solar radiation pressure acting on a large thin surface, like a solar sail? A flat, reflective object would experience tiny but measurable acceleration from sunlight. Photons carry momentum, and when they bounce off a reflective surface, they transfer that momentum. Solar sails are a proven technology. We've flown them successfully in Earth orbit and on interplanetary missions. If Oumuamua was a solar sail, or something like a solar sail, the acceleration would fit perfectly. The elongated shape would make sense. A thin, flat sheet would look elongated when viewed edge-on. The lack of visible coma would make sense. No outgassing because propulsion comes from radiation pressure, not sublimation. Even the tumbling rotation would fit. A damaged or derelict sail would tumble, rather than maintain stable orientation. This hypothesis came primarily from Avi Loeb, chair of Harvard's astronomy department. He wasn't claiming proof. He was arguing that the artificial explanation fit the data as well as or better than natural explanations, and therefore deserved serious consideration rather than automatic dismissal. The response was fierce. Most of the astronomy community rejected the hypothesis immediately, not based on evidence, but based on prior probability. Interstellar probes are extremely unlikely, therefore any natural explanation, no matter how contrived, is preferable to invoking technology. This is the Bayesian prior problem. If you start with the assumption that artificial objects are vanishingly rare, then you'll require overwhelming evidence before accepting an artificial explanation. And you can always invent natural explanations that are merely unlikely rather than impossible. But here's the thing. We don't actually know how rare interstellar probes are. We have a sample size of 0 confirmed artificial objects, which tells us nothing about the true frequency. They could be common, they could be rare. We literally have no data to constrain the prior probability. What we do have is observation. And when observations don't fit natural models well, when you have to keep inventing special cases and unlikely conditions to force the data into natural categories, maybe the prior probability you're using is wrong. Oumuamua left our solar system before we could gather enough data to settle the question. The debate continues. Natural or artificial? Comet with invisible outgassing or defunct solar sail? We'll probably never know for certain, but the parallels to Atlas are striking. Both objects came from interstellar space. Both show behaviors that strain natural explanations. Both require invoking unusual properties or special conditions to fit into conventional categories. Both have prominent scientists arguing they might be something other than what they initially appeared to be. The difference is that we have more time with Atlas. Oumuamua was discovered on its way out, giving us only weeks to observe it before it faded. Atlas was caught on approach, giving us months to study it through perihelion and beyond. That extra time should mean better data, more observations from multiple instruments, detailed tracking of how the object's behavior evolves, the opportunity to actually test hypotheses instead of just speculating. And yet we're not seeing that comprehensive analysis made public. We're getting the same pattern as Oumuamua, initial observations, brief statements emphasizing natural explanations, then silence while the object fades from view. Why repeat that pattern? Why not use the additional observation time to settle the questions that Oumuamua left unanswered, unless the answers are uncomfortable? Unless the detailed observations are revealing things that institutions aren't ready to discuss publicly? Unless we're seeing a repeat of the same cautious communication strategy that prioritizes avoiding panic over sharing knowledge? I keep coming back to specific details that don't make sense under natural comet models: the jet geometry, the orientation stability, the spectroscopic anomalies. Each one individually might be explainable with creative interpretation, but together, they create a pattern that looks less like a weird comet and more like something operating under different rules. Let me walk through a thought experiment. Imagine you're designing an interstellar probe. You want it to survey planetary systems, gathering data as it passes through. What features would it need? Propulsion, obviously. Some way to adjust trajectory, maintain orientation, perhaps slow down or speed up as needed. For an interstellar mission spanning thousands or millions of years, you wouldn't use chemical rockets. Too much mass in fuel. You'd want something more efficient. Maybe solar sails for fine trajectory adjustments using starlight. Maybe something we haven't invented yet. Communication. But you can't transmit back to your origin civilization across interstellar distances with any reasonable power budget. So the probe would be autonomous, gathering data, processing it locally, perhaps storing it for eventual retrieval or relay through other probes in a network. Instruments, cameras, spectrometers, particle detectors, whatever sensors you need to characterize the system you're visiting, pointed in specific directions, creating geometric patterns of observation that might look strange to anyone watching the probe from outside. And maybe a disguise. If you're visiting systems that might contain intelligent life, maybe you want your probe to look natural, to blend in, to avoid detection and potential interference. What better disguise than a comet? Icy exterior, sublimating as you approach the sun, creating a natural-looking coma that hides the machinery underneath. This is pure speculation. I want to be clear about that. I'm not claiming this is what Atlas is. I'm showing you how easily we can construct narratives that fit the observations if we're willing to step outside the "it must be natural" framework. The artificial hypothesis isn't inherently less scientific than the natural hypothesis. Both are frameworks for explaining observations. The question is which one fits the data better with fewer ad hoc assumptions. Natural comet hypothesis. Atlas is a comet, but with unusual composition that creates large dust particles explaining the anti-tail, an unusual internal structure that creates geometric jets, an unusual rotation axis orientation that maintains stable geometry through perihelion, and unusual activity patterns that don't correlate with solar heating. Artificial hypothesis. Atlas is a probe using directed propulsion to create the anti-tail, maintaining orientation through active control, producing geometric structures because it's designed rather than chaotic, showing activity patterns based on operational state rather than passive solar heating, which requires more special cases, which invokes fewer unlikely coincidences, which makes fewer assumptions about properties we haven't directly observed. I'm not saying the artificial hypothesis is correct. I'm saying it deserves consideration based on evidence rather than automatic rejection based on prior assumptions about rarity. And here's what bothers me most. The way institutions handled Oumuamua created a template for handling Atlas, emphasized natural explanations, downplay anomalies, avoid discussing alternative hypotheses publicly, wait for the object to leave, then maybe, eventually, publish the honest analysis in academic papers that most people won't read. It's a pattern. And patterns exist for a reason, either because the approach is correct and prudent, or because institutions have learned to protect themselves from controversy, rather than pursue truth wherever it leads. I don't know which, but I know the pattern is recognizable, and that recognition itself raises questions about whether we're getting the full story or a carefully managed version designed to avoid difficult conversations. The problem with scientific conservatism is that it works both ways. Yes, it prevents premature acceptance of extraordinary claims, but it also prevents timely recognition of genuinely new phenomena that don't fit existing categories. History is full of examples where scientific consensus delayed acceptance of observations that didn't match expectations. Continental drift, meteorites, ball lightning, rogue waves, all initially dismissed because they contradicted accepted models, all eventually confirmed when enough evidence accumulated that denial became untenable. How many observations did we miss or dismiss before accepting each of those phenomena? How long did the evidence have to accumulate before overcoming institutional resistance to paradigm change? Atlas won't wait for paradigm change. It's leaving the inner solar system now, fading with each passing week. Soon it will be too dim for detailed observation. The window is closing, and when it closes, we'll be left with the data we already have plus whatever observations get made in the next few months. That data will be analysed, papers will be published, hypotheses will be proposed and debated in academic circles, but the public conversation will have moved on. Atlas will be old news. The opportunity for broad engagement with genuinely anomalous observations will have passed. That's the tragedy here. Not that we might miss discovering an interstellar probe. That's uncertain and maybe unlikely. The tragedy is that we're definitely missing an opportunity for honest public discussion of how we evaluate evidence when observations don't fit our models. Because whatever Atlas is, it's showing us the gaps in our knowledge and the limits of our willingness to entertain uncertainty. It's revealing how institutions handle data that doesn't conform to comfortable narratives. It's demonstrating the difference between science as an ideal of following evidence wherever it leads, and science as a social institution that has to balance truth-seeking with public relations and risk management. And those revelations are valuable even if Atlas turns out to be a perfectly natural comet with weird properties. They're teaching us about ourselves and how we respond to mystery, about where our curiosity ends and our defensiveness begins, about the difference between skepticism and denial. I've been accused of sensationalism, of clickbait, of exploiting public interest in aliens to generate views and revenue. And maybe there's truth in that accusation. Maybe I am drawn to controversial topics because they're more engaging than routine observations. But I'm also genuinely trying to understand what we're seeing, genuinely comparing Atlas to known comets and finding the comparisons unsatisfying, genuinely asking questions that the official analyses seem reluctant to address. If that makes me a crank, fine. I'd rather be a crank asking real questions than a conformist accepting inadequate explanations because they're socially acceptable. The data deserves better. The observations deserve honest analysis without predetermined conclusions. The public deserves transparent communication about what we know and what we don't, instead of reassurances that everything fits models when it clearly doesn't. An Atlas deserves to be evaluated on its own merits rather than forced into categories, because those categories are comfortable and familiar, whether it's a comet or something else, whether it's natural or artificial, whether it's mundane or extraordinary. Those should be conclusions drawn from evidence, not assumptions imposed before the evidence is fully examined. That's all I'm asking for. Honest evaluation, transparent communication, willingness to acknowledge when observations don't fit models instead of contorting models to fit observations. Is that too much to ask? Apparently so, given the responses I've gotten. Apparently questioning whether Atlas is definitely a comet marks you as a conspiracy theorist or attention seeker, rather than someone legitimately trying to understand anomalous data. But I'll keep questioning anyway, because the images don't lie. The comparisons are stark, the anomalies are real, and pretending they're not, dismissing them with hand-waving about unusual composition or exotic conditions, doesn't make them go away. It just means we're choosing comfort over curiosity, and I'm not willing to make that choice. Not when the data is this interesting, not when the questions are this important, not when we have an opportunity to learn something genuinely new, if we're brave enough to look at the evidence honestly. The silence from certain quarters is deafening, and by silence, I don't mean lack of statements, I mean lack of engagement with the specific anomalies that anyone looking at the data can see. Professional astronomers have published papers on Atlas, spectroscopic analyses, orbital dynamics, brightness measurements, all perfectly valid contributions to the scientific literature. But read them carefully, and you'll notice something missing. They describe observations without addressing the fundamental questions those observations raise. A paper will note the anti-tail's persistence, but won't explain the mechanism that allows it to resist solar wind for months. Another will document the jet geometry, but won't discuss why rotation doesn't affect it. A third will analyse the composition, but won't address why the volatile ratios don't evolve as solar distance changes. Each paper treats its narrow topic professionally, presents data carefully, draws limited conclusions appropriately, but collectively, they're avoiding the elephant in the room. They're describing pieces of the puzzle without acknowledging that the pieces don't fit together into a coherent picture of a natural comet. This is how institutional science handles uncomfortable data, not through conspiracy or cover-up, but through fragmentation. Divide the anomaly into small enough pieces that each piece individually seems unremarkable. Publish papers on each piece separately. Never step back and look at the whole pattern. Never ask the integrative questions that might lead to uncomfortable conclusions. It's professionally safe. You can't be accused of speculation if you're just reporting measurements. You can't be dismissed as a crank if you're staying within the narrow bounds of your specific analysis. You can't damage your career by writing papers that scrupulously avoid drawing the larger conclusions that the data might suggest. But it's intellectually dishonest, because the larger pattern matters. The way multiple anomalies cluster in a single object matters. The fact that this isn't just one weird feature but a constellation of unusual behaviours matters. And avoiding discussion of that pattern because it might lead to uncomfortable conclusions is cowardice dressed up as rigour. I've reached out to several researchers working on Atlas. Polite emails asking about specific aspects of the observations, the jet geometry problem, the perihelion orientation question, the compositional stability issue. Most don't respond. A few send brief replies that essentially say, "Interesting question, we're looking into it," without providing any actual insight. One researcher was more candid. Off the record, not for attribution, they admitted that several teams are seeing things in the data that don't fit standard models. But nobody wants to be the first to publish something that challenges the comet classification. The professional risk is too high. The potential for being wrong and looking foolish outweighs the potential for being right and advancing knowledge. So they wait. They gather more data. They run more models. They refine their analyses. And they hope that eventually someone else will stick their neck out first. Or that the anomalies will resolve themselves as more observations come in. Or that the object will fade from view before they have to commit to any interpretation that might prove controversial. This is how discovery gets delayed. Not through malice, but through caution. Not through conspiracy, but through careerism. The incentive structure of modern science rewards safe, incremental work and punishes bold claims that might turn out wrong. And I get it. I understand why individual researchers make the choices they make. Nobody wants to be the next person who claimed extraordinary findings only to have them debunked by follow-up observations. Nobody wants to be remembered as the astronomer who cried alien when it was just a weird comet. But collectively, those individual safe choices create a systemic failure. Important questions don't get asked publicly. Anomalous data doesn't get integrated into coherent hypotheses. And we end up with a literature full of careful descriptions of individual observations but devoid of the synthetic thinking that might actually advance understanding. Let me show you what this looks like in practice. There's a paper from last month analysing Atlas's dust colour, spectrophotometry, across multiple wavelengths, measuring how the reflected light spectrum changes with observation geometry. Solid methodology, good data. Careful analysis. The conclusion? Atlas's dust has unusual colour properties compared to typical comets, slightly redder in certain wavelength ranges. The authors suggest this might indicate different dust composition or grain size distribution. Fair enough. But here's what the paper doesn't discuss. Why would an interstellar comet, supposedly formed in conditions similar to our outer solar system comets, have significantly different dust properties? What about its formation environment would create this compositional difference? And how does this unusual dust composition relate to the unusual structural features like the anti-tail and geometric jets? Those questions aren't addressed. The paper presents the colour measurements as an isolated curiosity without connecting them to the broader pattern of anomalous behaviour. It's a data point floating in isolation, disconnected from the larger mystery. Another recent paper examined Atlas's rotation period. Multiple observations over several weeks, careful light curve analysis, determination that the period is approximately 7.8 hours, professional work, useful contribution to the literature. But the paper treats rotation as if it's independent of the other observed features. It doesn't ask why a rotating nucleus produces jets that don't fan out. It doesn't address the orientation stability problem through perihelion. It presents rotation as a simple measurable quantity, without engaging with the puzzles that rotation creates when combined with the other observations. This is the pattern. Careful measurements of individual properties, professional analysis within narrow scope, conclusions that avoid synthesis or integration with other anomalous features, death by 1,000 careful papers, each one individually defensible but collectively missing the point. Compare this to how we handled Oumuamua. After the initial observations, after the acceleration was measured and the outgassing explanation proposed and found wanting, did we get honest acknowledgement that we didn't understand what we were seeing? Did we get papers saying, this object's behaviour doesn't fit our models and we need to consider alternative hypotheses? No, we got increasingly elaborate natural explanations, pure nitrogen icebergs, cosmic dust bunnies, hydrogen icebergs that would sublimate invisibly, each explanation more contrived than the last, each one requiring special conditions we've never observed elsewhere, and all to avoid saying, we don't know what this is. And when Avi Loeb suggested we should seriously consider the artificial hypothesis, not as proven fact but as a possibility worth investigating, the backlash was immediate and harsh. He wasn't just disagreed with, he was dismissed, mocked, accused of seeking publicity rather than doing science. The message was clear: stay within acceptable bounds. Don't suggest extraordinary explanations even when ordinary explanations require extraordinary assumptions. Preserve the conventional narrative even if you have to twist the data to fit. That's what Atlas is getting. The same treatment. The same careful avoidance of synthesis. The same reluctance to acknowledge that maybe our initial classification was wrong. And the clock is ticking. Every week Atlas gets dimmer. Every passing month reduces the quality of observations we can make. Soon it will be beyond the reach of all but the largest telescopes. Then it will be gone entirely, leaving us with whatever data we've already collected and whatever analyses we've already published. Is that data set sufficient to answer the hard questions? I don't think so. We haven't deployed the observational resources that an object this anomalous deserves. We haven't coordinated the kind of comprehensive multi-instrument campaign that might actually resolve the mysteries. Why not? Partially resource constraints. Telescope time is precious, and directors are reluctant to dedicate significant resources to an object that might turn out to be just a weird comet. Partially professional conservatism. Why risk your reputation and your telescope allocation on a potentially controversial object when there are safer targets available? But partially, I suspect, because a comprehensive observational campaign might produce data that forces uncomfortable conclusions, might reveal details that can't be explained away with vague references to unusual composition or exotic conditions, might document behaviours that definitively violate natural comet physics, and if that happens, if we gather incontrovertible evidence that Atlas isn't what we're claiming it is, then what? The institutions that have been reassuring the public that everything is normal, that Atlas is definitely just a comet, that there's nothing to worry about, those institutions would have to admit they were wrong. Or worse, admit they knew there were anomalies all along but chose not to discuss them publicly. The loss of credibility would be significant. The public relations fallout would be severe. Better to avoid gathering the definitive data in the first place. Better to let the object fade while maintaining plausible deniability. Better to preserve institutional credibility by never fully testing the claims you've been making. I sound paranoid. I hear it in my own words. The conspiracy theorists seeing patterns that aren't there, attributing coordination and intent to what's probably just ordinary professional caution and resource constraints. Maybe that's what this is. Maybe I'm reading too much into normal scientific conservatism. Maybe the lack of comprehensive observation isn't strategic avoidance, but simple prioritization of limited resources. But then I look at the images again. I compare Atlas to real comets. I see the differences that are undeniable regardless of interpretation, and I can't shake the feeling that something important is being overlooked or ignored, because acknowledging it would be professionally and institutionally uncomfortable. The geometry doesn't lie. The straight jets are visible in the processed images. The anti-tail's persistence is documented across multiple observation sessions. The lack of conventional dust and ion tails is obvious when you look at comparable images of real comets. These aren't subtle features that require expert interpretation. These are obvious visual differences that anyone can see if they bother to look. So why aren't more people looking? Why aren't more researchers publicly asking the questions that the images provoke? Fear. As career preservation, institutional pressure to conform, the knowledge that challenging accepted narratives, even with good evidence, carries professional risk. Science is supposed to be self-correcting. When new evidence contradicts old models, the models get revised. That's the ideal. The reality is messier. Models get defended. Anomalies get explained away. Paradigm change happens slowly, grudgingly, only when the evidence becomes too overwhelming to ignore. And in the meantime, individual researchers who point out problems with the current model get marginalized, dismissed, accused of attention-seeking or poor judgment. I've experienced this personally. The response to my Atlas videos hasn't been interesting observations, let's discuss the data. It's been, you're being sensational, you're cherry-picking, you don't understand cometary physics, you're exploiting public interest for views. Maybe some of that criticism is valid. Maybe I am emphasizing the mysterious aspects while underplaying the mundane explanations. Maybe my lack of formal credentials in planetary science means I'm missing obvious things that experts would recognize. But the experts aren't offering those obvious explanations publicly. They're not publishing papers that definitively resolve the anomalies. They're not providing the detailed physical models that show how natural processes create the observed behaviors. They're just asserting that natural explanations exist, that the anomalies aren't as significant as they appear, that everything makes sense if you understand the complexity of cometary physics. Trust us, they say. We know better than you. Your concerns are based on incomplete understanding. And maybe that's true. Maybe there are sophisticated models being developed that will explain everything once they're published. Maybe the experts really do have insights that resolve all the puzzles, but until those explanations are made public, until someone shows me the actual physics rather than just asserting it exists, I remain skeptical, because I can see the images, I can compare them to other comets, and the differences are stark. This isn't about me being smarter than professional astronomers. I'm not. This is about images showing things that either fit the comet model or don't, and from where I'm sitting, they don't fit. The rotation problem alone should be enough to generate serious papers addressing the mechanism. How does a nucleus rotating every 7.8 hours produce jets that show no spiral structure? What configuration of vents? What pattern of outgassing? What peculiarity of the nucleus could create straight-line jets despite rotation? That's not a rhetorical question. That's a real physics problem that deserves real analysis. And I haven't seen that analysis published anywhere. The perihelion orientation problem is even more stark. The geometry is simple. The pole's relationship to the Sun changed by 16 degrees when Atlas passed perihelion. For the anti-tail to maintain its sunward orientation, either the nucleus adjusted its rotation axis by exactly that amount, or there's a matching vent on the opposite pole that happened to activate post-perihelion. Both scenarios are wildly improbable for natural processes. One requires unexplained torque. The other requires absurd coincidence. Neither has been addressed in the published literature beyond vague hand-waving about possible rotation axis precession. Show me the model. Show me the physics. Show me how natural processes create either of those outcomes with probability high enough that we should expect to see it in a single interstellar visitor. Nobody's showing me that because nobody's published it. And I suspect nobody's published it because the analysis doesn't work. The natural explanations don't actually hold up when you do the detailed modelling, so we get silence instead. Or rather, we get careful descriptions of observations without synthesis into coherent models. We get individual data points without integration into testable hypotheses. We get professional caution instead of scientific courage. And Atlas fades. And the opportunity passes. And eventually we'll be left with a literature full of measurements but empty of understanding, a collection of puzzle pieces that nobody assembled because assembling them might reveal a picture we weren't ready to see. That's the real tragedy. Not that we might miss discovering an interstellar probe, that's speculation, and maybe unlikely. The tragedy is that we're definitely missing an opportunity to practice honest science, to follow evidence wherever it leads, to acknowledge when our models don't fit and to seriously consider alternatives instead of defensively protecting established categories. I started this investigation thinking I'd find reassuring explanations, thinking that once I understood cometary physics better, the anomalies would resolve and I'd feel foolish for ever questioning the comet classification. The opposite happened. The more I learned about how comets behave, the more Atlas's behaviour stood out as anomalous. The more I compared it to real comets, the less it looked like a comet. The more I asked for explanations, the more I encountered silence or hand-waving, and now I'm here, convinced that we're seeing something genuinely unusual. Not certain what it is, but certain that the standard explanation doesn't fit, frustrated by institutional reluctance to engage with that uncertainty honestly. Maybe I'm wrong. Maybe future publications will explain everything. Maybe I'll look back on these videos embarrassed by my misunderstanding and overconfidence. But maybe not. Maybe the anomalies are real. Maybe the silence indicates discomfort rather than confidence. Maybe we're watching something unprecedented while being told it's routine, and if that's the case, if we're missing genuine discovery because acknowledging it would be professionally uncomfortable, then we've failed not just as scientists but as curious beings willing to confront the unknown. Whatever Atlas is, it deserves better than that. The data deserves better. The public deserves better. And science as an institution deserves to live up to its ideals instead of retreating into defensive conservatism when observations challenge comfortable narratives. That's what I'm fighting for. Not proof of aliens or vindication of any specific hypothesis, just honest engagement with anomalous data. And just willingness to say we don't know when we don't know instead of pretending we do. Just science practiced with courage instead of caution. With curiosity instead of conformity. With commitment to truth instead of comfort. Is that too much to ask? Based on the response I've gotten, apparently yes, but I'll keep asking anyway. Keep looking at the images. Keep comparing to real comets. Keep pointing out the differences that anyone can see if they're willing to look honestly. Because the alternative, accepting inadequate explanations because they're socially acceptable, is worse than being wrong. It's intellectual surrender. It's choosing comfortable lies over uncomfortable uncertainty. And I'm not willing to make that choice. Not while the images keep showing me things that don't fit the narrative I'm being told to accept. Not while questions keep going unanswered because asking them is professionally risky. Not while genuine mystery gets papered over with reassurances that everything makes sense when it clearly doesn't. Atlas will fade. The data will be what it is. The analyses will be published or they won't. But the questions I'm asking, about how institutions handle anomalous data, about the difference between skepticism and denial, about the courage to acknowledge uncertainty, those questions will remain relevant long after Atlas is gone. Because they're not really about Atlas, they're about us. About how we respond to observations that don't fit our expectations, about whether we're willing to follow evidence into uncomfortable territory or whether we retreat into familiar narratives. And the answer to that question matters for far more than one mysterious object passing through the solar system. It matters for how we do science, how we communicate with the public, how we balance truth-seeking with institutional preservation. Atlas is teaching us those lessons whether we're ready to learn them or not. The only question is whether we're paying attention. I am, and I hope you are too. Because this matters. Not just the specific mystery of what Atlas is, but the larger question of how we handle mystery when it appears in our carefully categorized universe. Do we embrace it, or do we explain it away? Do we investigate honestly, or do we protect comfortable narratives? Do we follow evidence, or do we follow convention? The choice we make with Atlas will set the pattern for how we handle the next anomaly, and the one after that, and every future observation that doesn't fit neatly into our existing models. Choose courage, choose curiosity, choose honest uncertainty over false certainty. That's what science is supposed to be. That's what Atlas deserves, and that's what we owe ourselves. Thank you for watching, for thinking critically, for being willing to look at evidence honestly even when it's uncomfortable. Hit that subscribe button if you want to keep following this mystery and others like it. Leave a comment with your thoughts. Do the anomalies concern you? Have I missed obvious explanations? Are you seeing what I'm seeing in these comparisons? And if you can, support this work through Patreon. Independent analysis costs time and resources. Your support makes it possible to keep asking questions that need to be asked, even when they're professionally uncomfortable. Until next time, stay curious, stay skeptical, and never stop demanding evidence instead of accepting reassurance. Whatever the truth about Atlas turns out to be, pursuing it honestly matters more than reaching comfortable conclusions.